You let me know where to. Yeah, just you let me know when to start. Okay, thank you. Hello, everyone. My name is Hamza Jaâfar, and I'll be reporting on a joint work with Guilhem Jaâfar. And it's a work in which we aim to find a fully abstract model of the operational gauge semantics kind for language with algebraic effects and handlers, and in which we have the possibility to dynamically generate effects. So, for operational semantics, we've seen some talks thus far, and I'll try to start by talking what type of language we're interested in. So I'll start by a brief introduction, like to tracing the semantics origins of algebraic handlers. They appeared in the work of Plotkin and Power, where the impure behavior arises from a set of operations, and these operations act on computations, and one can think of non-determinism, exceptions, and state, and so on. And the behavior of the impure behavior is described given by an equations on that are satisfied by these operations. So given an algebraic theory, and since every algebraic theory corresponds a monad, they account for a lot of monadic effects, specifically those whose operational behavior does not depend on the current evaluation context. So in a sense, this can be captured by the fact that operations and continuations commute. Here I give an example of a choice operator. And their main selling point is that they are easy to combine and to structure effects compared to combining monads. So, and in this very algebraic setting, handlers just are maps between two models, or specifically like the unique homomorphism between the free model to another model of an algebraic theory. So the way then we turn this into a nice programming language in which we assume a set of operations that are constructors or producers effects, and then we have these handlers which are context that will give semantics to these operations. And there are some sort of generalizations of exception handlers. Generalization in the sense that not only the effect is got, but also the delimited continuation. So that can be used subsequently. So more concretely, a language will be equipped by a set of operations that comes with a narrative. Here, tau, arrow, sigma, which should be read as the operations expect this operation op expects a parameter of type tau, and it should return something of type sigma. And to perform an effect, we just apply it to a value of type tau. And to handle it, we have these contexts that will look at two cases. So we have two clauses. If the enclosed continuation returns a value, then for here the first clause, the value will be bound to x in n. And if the enclosed continuation performs an effect, then the parameter would be bound to p, and the continuation, the delimited continuation, will be bound to kappa in the m. And then we resume evaluation. So we're interested in a typed setting. So in a typed setting, effects will be given a type that is essentially just the set of operations that they're involved in, and with their respective arities. So a typical example will be state, a state in which we want to store something of type tau. So we'd have the standard operations set and get. But sometimes we want two states. So one way of doing this is to have two types for the first state and the second state, and we have like two set of operations, set one and get one, and set two and get two for the second state or memory cell. But that is not very modular. So a question that arises is, how do we deal with multiple occurrences of the same effect without losing modularity? There are a lot of answers that have been proposed, from lexically scoped handlers to coercions, so constructs that are added to the language, but we choose a simpler approach given in the F language, which is due to Pretnar and Andre Bauer, in which we use distinct identifiers for each instance of effect. Here we call it iota. So everything that I said thus far still holds. We just, when we want to perform an effect or handle it, we specify at which instance we're dealing with. And these instances, we want them to be like first-class values that we want to exchange. So these are the main bricks for the type of language we are interested in. So I'll just give briefly over the syntax. It's just a fine-grained call by value. Call by fine-grained in the sense that we have a distinction between computations and values. Here we see that we add to the values instances, which are first-class values that will be exchanged by the program and its environment, and we add to the computations all the mechanism to perform effects and handle them by giving the appropriate evaluation context. So, as I said in the beginning, we are interested in the dynamic generation of effects. So, how we do that? We follow again the approach of F, or the original F approach, which is having this new constructor that will generate fresh effects, and we give it the reduction rule that is standard. It just, whenever we have new, we just generate a fresh instance and associate it to a certain effect, and then we return it. And here we have also an added component just to keep track of instances that have been played, that have been generated. So, so the thing here we have a notion of this notion of disclosure, because we generate something that is new, so it's not necessarily private. It's not necessarily public because it has not been yet disclosed to the environment. So these instances have this private and public status, which have something like could affect the contextual equivalence, because as we said, we're trying to find a fully abstract model with respect to contextual equivalence. So I'll try to give this to show these subtleties by way of an example. Here we have a simple open term. F is applied to the constant function that always returns 5. And as it turns out, it is contextually equivalent to this slightly bigger term. So just let's break it down. It just creates a fresh instance. And then inside a nice handler, what happens is we apply f to yet again another constant function that always performs an effect associated with this instance. So we can think of scenarios. If f doesn't use its argument, then both will behave the same as the value. As we can see, the return clause of the handler, it just propagates the value, so they behave the same. But what if f uses its argument? It uses it applies it to something, gets 5, and continues for the first term. For the second term, what happens? It applies it. An effect will be performed. F cannot handle it because it's freshly generated instance. So it's going to be captured by the handler, which will also capture the continuation of f. And here in this example, what the handler does, it just passes 5 to the continuation. So in both cases, we just continue with 5, so they are equivalent. And the key point here is that the reason they are equivalent is because this fresh generated instance has remained closed in this, has remained private in this example. It has not been disclosed to the environment. So if we consider a variation in which the instance is passed to the environment, we have a term that depends on two things from the environment, the function g and the f. But when we create the instance, we pass it to g before applying f to the same constant function. Here, if we do the same trick and wrap it around, apply f to a different function and wrap everything around the same handler, these two terms are no longer equivalent because the secrecy has not been maintained, and we can think of a context that will use this information to discriminate between these two terms. So now we're trying to find an operation game semantics model that captures these subtleties. But before, I'll have a word on existing work that tries to do something similar. There's an abstract, fully abstract. There's a fully or complete characterization of contextual equivalence given by Biernatsky and co-authors in the form of normal form dissimilarity, and I think we've heard about it this morning in previous talks. So it's a refinement of Lassen's normal form assimilation. And the difference between our work is that in their setting, their calculus is untyped, and they just assume a set of operations. And what is interesting in that paper is that their completeness proof does not rely on do not assume the full power of references that is usually done in these cases, but it all just relies on hundreds and fx, and we hope to achieve something similar with this work without assuming more things in the language. But it's slightly complicated to lift this to a setting in which we have local names and generativity. So let's briefly sketch what are operational game semantics. It is a game semantics, so program is a player, seen as a player, interacting with the environment, and it's essentially trace semantics, and the interaction is given by traces, which are alternating sequences of player moves and opponent moves. These are the dual moves. So these moves have two shapes, is questions, where in previous talks they were called like calls and returns, so questions are just calls. And F applied to A and C, which should be read as the player is requesting the result of the application of F to A in the continuation named C. And there's also returns, in which we just return a value A in the continuation named C. So I'll just try to give the intuition of how these traces can be built by way of an example. So let's consider our first example, and let's see how it interacts with the environment, which instantiates F with this function. It takes a function G, applies it to something, discards the result, and just returns true. So it's already in normal form. We start by asking the environment what is the application of F to G, which corresponds to the constant function. The environment, what we'll do, it just applies it to a value and then expects a result in D. It's the constant function, so we will return 5, then giving control back to the environment, which will end up returning true in the unanswered continuation named C. So a general way of doing things is by label transition systems on open terms or normal forms, as it has been explained in the previous talk. So we start by just looking at normal forms that we have in a language, and with the strategy, here a call by value strategy, normal forms are either computation stuck on an application that depends on an environment, or a return value. So the stuck application will call for a question, and here we expect a result in C that is supposed to represent the evaluation context E. And the other case is just return a value answering the last non-answered continuation. And by doing this, we have this whole label transition systems that I will not go into details to show. And the denotation of a program is basically just the set of all possible traces that this interaction generates. And what we want to capture is that two denotations are the same if we want this two denotation to be the same if and only if two programs are contextually equivalent. Let's extend this to algebraic effects. So we have a new added normal form, but as we can see in our context, it depends on this iota that could be private or public. So the natural way is just to extend the moves of this LTS to account for observable effects, but it's worth asking the question, what is an observable effect in this scenario. I'll explain briefly. If a program performs an effect here at instance iota, it depends on the status of iota what opponent is able to do. If it is public, then opponent could potentially handle it. If it is private, then he can only forward it, and in the same time, pass is like give the communication its continuation to the player. So we just follow this idea and see what we can add to this LTS. If there's an observable effect, then we have this move that answers with an observable effect, the same instance and operation. We give access to the parameter, and we also give access to the continuation by this name called kappa that could be used by the environment. And we also add in the LTS the dual move that corresponds to opponent. If it's private, then opponent can do nothing. So we just skip its transition and just forward its continuation to the original player. I'll hope this will be clear in a small example. But before, I just want to recall that our nice example that we had in the beginning, called the term M1, generated this trace when we made it interact with this environment. And we also said that this term is equivalent to this slightly bigger term. But let's look at how this other term interacts with the environment, with the same environment. So it generates a fresh instance, and then it evaluates to this normal form that we see on the screen here. Here it's stuck on an application, so it starts by asking a question. The environment will just apply it to a value and expects a result in D. Since it is this G will perform an effect on an instance that is private, what would happen is just nothing. It's just the continuation of the opponent would be forwarded to the player, and we go back to the closest enclosing environment evaluation context. And as it turns out, this evaluation context is the handler. So this effect would be handled, and continuation would be past 5. But a fragment of this continuation depends on the D of the opponent. So what would happen? You just pass 5 to the opponent, and we ask it, what's the result? And then he regains control and gives us true. So at the end, we have two terms that are contextually equivalent, but the set of traces are not the same, because we have these different, they generate different traces. So the thing is, our traces are too intentional, and we need a way to relax them, and a nice way to find a new equivalence on a set of traces. We managed to, I will spare the details, but the idea is just to have some canonical representation of traces by some rewriting rules, where we get rid of almost all the forward moves, and then an extra step where there are some permutations of the forward moves that I can't get into details. So we have a nice definition, recursive definition of this equivalence. So as for the result, we show that this trace equivalence, this new refined trace equivalence, it actually implies contextual equivalence. So the model is sound, and we conjecture that it is also complete, and because it's we do the standard way of going with the definability result, and there's some technical difficulties there. So in conclusion, what we did is that we saw that contextual equivalence gets a bit it's more difficult when we have first-class instances and generativity for these instances, and we have extended the standard models of calls and returns to account for effects that are observable and also private, which are just control flow, like control operators, more or less. And we find a way to relax the trace equivalence because it was so intentional, so that it could coincide with the contextual one. Thank you. I'll be happy to take questions.
Thanks. We have time for maybe for one question, and I would also like to ask the next speaker to start preparing. Yeah.
Yeah, I had a question about your conjecture that you've got the completeness of the trace equivalence and the contextual equivalence. So, I mean, that would kind of surprise me, because thinking about in operational game semantics, you're kind of looking at like you often have a model of a labeled transition system, and in the world of concurrency, when you have trace equivalence, that's often a weaker notion than contextual equivalence, and a weaker notion than bisimilarity, and it often comes out when you look at branching behavior of processes. So I wondered if you had any comments on why you think it will hold in the other direction.
I don't have enough intuition about concurrency, but I think the reason it should work because these transitions are not like in a sense are hidden from the environment. So even though there's subtlety, like they're necessary in order to construct a full trace, but observationally they are like we can permute them, we can remove some of them. They are observationally like not useless, but they are hidden from the opponent that will observe them. I don't know if that answers.
I'm not convinced, but it's just
Okay.
my intuition versus yours. So yeah, it's a good answer, I think. Yeah.
And it's also like there's no counter example, and the proof almost works. So I don't see why it will.
Okay. Yeah, if we have more questions, I think we can take them at the next break. Thanks. Thanks again. So the next talk is by Peyo Bordel, and
it's about what I can't see any slides.
Ah, I see. Now? No.
Yeah, I can't see any. Oh, that's okay, can I not straight?
Yeah. No, this will be fine. Yeah, okay.